Hey guys, so today we're going to be going one step further. In the last video, we talked about how to dilute solutions and the math involved in creating a diluted solution. In this video, we're going to look at if we had a solution that we don't know the concentration of, how can we experimentally determine the concentration of that solution? We're going to look at two different techniques today, and then we're going to look at another one in a future video as well. But here's the key. In today's video, we're going to look at spectrometry, which is how we look at light absorbance and transmission. And we're going to look at conductivity, which is how the solution conducts electricity. Both of these properties are impacted by the concentration of the solution. And so we can use them to actually determine the concentration of unknown solutions. Let's start with spectrometry. Now, in light spectrometry, what we're going to do is we're going to shine a light through a solution and determine how much of that light is going to be transmitted through the solution or absorbed by the solution. Now, if a solution is going to absorb light, that means that the light that is being absorbed will not make it through to the other side. That's similar to the idea that my shirt absorbs light. In this case, my shirt is absorbing every wavelength of light of color that it is not. So we see only what's reflected. In solutions, we see only that which is transmitted. So what we see is effectively the light that's coming through the solution and not the light that's being absorbed by the solution. So if we see a red solution, it'll transmit only red light and it'll absorb at every other wavelength. And the concentration of the solution is going to dictate how much of that light it absorbs or allows through. The more concentrated a solution is, the more light it's going to absorb. There's actually an equation called the Beer's law equation that is going to be on the formula sheet. And the Beer's law equation tells us exactly that the more concentrated a solution is, the more light it's going to absorb. In fact, here's the Beer's law equation. A, which is absorbance, is equal to little a, which is molar absorptivity, which is essentially this particle that you're looking at, how much would it absorb if there was only 1 mole of it, times B, which is path length. So in other words, if I shine a light through a very narrow path, it's going to absorb less than if I shine light through a much longer path, times C, which is concentration. Now, experimentally, we keep A, little a, the molar absorptivity, and little b, the path length, the same. We keep path length the same because we use what are called cuvettes in our spectrometer. Now, our spectrometer is going to shine a light through one side of the cuvette, and there is a sensor on the other side of the cuvette where it's going to measure exactly how much light of every wavelength made it through that solution. We will then see the recording output on our computer screen. The key to spectrometry is the fact that you need to be able to understand where that solution lies in terms of its relative concentration. So in order to do this properly, we have to use standard solutions. These are going to be solutions that we create ourselves with known concentrations. If we can create solutions with known concentrations, we can then match it knowing that it's a direct relationship between the solution concentration and the light absorbance. We can then determine, hey, I know if I've got a solution of this concentration, this is how much light will be absorbed. So therefore I can take the light absorbance and connect it back to the concentration if that's the data we can collect. Okay, so let's look at a practice problem where we take the relative absorbance of a solution and try to find the concentration given what we know about that solution. All right, so now I've had a couple of seconds to work through the problem on your own. Let's work through it together. I've given you some information, and we're simply going to take that information in this situation and plug it into our Beer's law equation. I've given you the absorbance of 0.54, the molar absorptivity of 6.4 times 10 to the third. I've given you the path length of 0.5, and we're looking for C, or concentration. So in this situation, we're simply going to plug and chug into our Beer's law equation. So let's go ahead and do that. We solve for x. So now we know that our concentration was 1.69 times 10 to the negative 4 moles per liter, or molar. So this is one way that we can use Beer's law to solve for concentration. Let's talk about the other way now. Now the second way to use Beer's law is with actual data using stock solutions. Now, we're going to do this in actually a laboratory this year, but here's the idea. If we know the concentration of certain solutions, we can then use those concentrations and match them against their absorbances. So we take a known concentration and we identify the absorbance of that thing. Then what we can do is create a line of best fit. This is going to give us the ability to then say, okay, well, we've got this y equals mx plus b relationship, right? Or that of a straight line. Well, just like you can use your x to solve for y, we can also use our y to solve for x. So if I have an unknown concentration solution, what I can do is say, well, let me measure the absorbance. Let's say I measure the absorbance to be right here. I can then take that, I can come across and then down. And with that, I can identify the concentration of that unknown solution. So this is our second way of measuring Beer's law, or using Beer's law to actually measure experimentally the concentration of an unknown solution. Now, be aware, because Beer's law is a direct relationship, you're always going to be dealing with a straight line. The only question is, at what slope, and what is the relative relationship between the percent absorbance and that concentration. So what we can do is simply use this line to make a prediction of our concentration given a known absorbance. So now that we've experimentally measured the concentration using light absorbance and transmission, the technique of spectrometry, we're going to do it in the second way. Now the second way we're going to discuss today is going to be measuring the concentration using conductivity. Conductivity is essentially the ability of a solution to conduct electricity. If we look at an ionic solution, what we know is that it can conduct electricity more efficiently if there are more ions present. Well, more ions present suggests more concentrated. So we know there is a relationship between conductivity and concentration of ions. So for ionic solutions, we can actually use conductivity as a measure. Now, unlike with light absorbance and transmission, there's no equation that I need you to know for this, but you do need to understand the general trend. And so the general trend is, as I mentioned again, if you are more concentrated, you are a better conductor of electricity. But remember, you can only use conductivity as a measure of concentration in ionic solutions. Covalent solutions, such as sugar water, won't conduct electricity no matter what the concentration, and that's because the ions are required to transfer electrons from one side of the solution to the other. So that wraps up today's video. Let's do a quick recap. We looked at two techniques in order to measure the concentration of solutions experimentally. The first one used Beer's law in light spectrometry, where the absorbed light is going to change relative to the concentration. If you double the concentration, you change the amount of light absorbed. Secondly, we looked at the relationship between conductivity and concentration. The more concentrated a solution is, the more electricity it will conduct. But remember, that's only with ionic solutions. I'd like to thank those who wrote, filmed, and edited this video. Cynthia Schwady, Sydney Judd, and Faye Durant. I'd like to thank you guys for watching, and I'll see you in the next one.